All right, team, let's dive right in. We're here today for a critical design review on our next generation engine cooling strategy. What we decide here is going to directly shape the capability of our future high-performance vehicles, so let's get focused. Here's the number that's driving this entire conversation: 40 kilowatts. That is a massive amount of waste heat. Think of it as the thermal load we'll see when one of our new engines is towing a heavy trailer uphill on a blistering hot day. This isn't a nice to have. It's the new performance target our engine oil cooling system absolutely has. And just to be crystal clear, our current systems, they just weren't built for this. They top out around 25 kilowatts, maybe a little more on a good day. The market is demanding more power, and that gives us a very clear engineering mandate. We have to solve this thermal challenge, period. So here's our game plan for this briefing. We'll start with why things are getting so hot. Then we'll review our core technologies, water versus air cooling, and get into the data on some new concepts we simulated. From there, we hit the really tough part, the packaging puzzle. We'll weigh performance against practicality, and I'll lay out our recommended path forward. Okay, first up, the future is hot. Let's dig into exactly why we're being forced to come up with an entirely new cooling strategy. The driver is simple, really. It's power. The market, and by extension our product planners, expect future diesel engines to push past 200 kilowatts and our petrol engines to blow past 350. And they have to do that while towing more than ever before. You know as well as I do, more power, especially under heavy load, means more heat. A lot more heat. All right, so let's get back to basics for a second and look at the core technologies we have in our toolbox. Water versus air cooling. We've got two primary methods on the table. First, there's oil to water, or OTW. This is the workhorse we're all familiar with. Its biggest advantages: it's compact, and it's pretty flexible to package. The downside, of course, is that it dumps all that oil heat directly into the main engine coolant, which just puts more strain on the primary radiator. Then you've got oil to air, or OTA. It's a much more direct and efficient way to reject heat. But it's bigger, and, this is key, it has to be placed right in the path of clean airflow to do its job. Okay, section 3. This is where we get into the data. We've run several new concepts through simulation to see how they actually perform against that 40 kilowatt target. Now, let's look at an early idea we called Concept 4. The theory here was to add a water-to-air cooler to basically pre-cool the engine coolant before it hit the main oil cooler. And you can see from the simulation data, it's definitely an improvement over stock, but it's not the whole solution. At the kind of airflows we can realistically expect, it's peaking around 35 kilowatts. It gets us closer, but it doesn't get us to the finish line. And that brings us to the concept that's showing the most promise. It's a hybrid approach. We keep our current proven oil-to-water system, but we add an additional oil-to-air heat exchanger in series. The OTW handles the baseline load, and the new OTA unit comes in to handle the extreme heat that the old system just can't manage on its own. And this table really tells the story. The numbers don't lie. Our current system taps out at 25 kilowatts. That water-to-air idea, Concept 4, gets us to 35, but look at the airflow it needs. Over 1.2 kilograms per second. That's just not realistic in many conditions. Now look at the series OTA concept. It blows past our 40 kilowatt target, and it does it at just 0.7 kilograms per second of air. That efficiency at lower airspeeds is absolutely crucial for scenarios like low-speed rock crawling or pulling a boat up a steep ramp. This is the winner from a thermal perspective. So we have a thermal solution that works on paper. Fantastic! But now comes the part that keeps us all up at night. Where in the world do we physically put this thing? Welcome to the vehicle packaging puzzle. Let's be blunt, we have a concept that hits the performance target. The engineering works. The challenge for this team right now is packaging. And here is the problem in plain sight. Our CAD analysis points to one spot as the most promising location for this new OTA cooler, right here behind the left front bumper. It's got the best combination of available space and potential airflow. The problem? That exact real estate is already occupied by the engine control unit and the engine's main air intake. So we have a conflict. Which of course leads us right into the classic engineering balancing act: performance versus practicality. Every single choice we make has a downstream consequence, and we need to understand the real-world trade-offs of this solution. This quote explains perfectly the vicious cycle we're trying to break. When the engine gets too hot, the ECU protects it by pulling ignition timing. To make the same power with less timing, you have to inject more fuel. More fuel means more combustion, which means, you guessed it, even more heat.
Our cooling problem is directly tied to fuel efficiency under load.
And if you want a perfect real-world example, just look at the Bronco lineup. A standard Bronco gets a respectable 20 mpg combined, but the high-performance Raptor, with all its beefy hardware, huge tires, and compromised aerodynamics, drops to 15 mpg. Every component we add, especially a new heat exchanger hanging out in the airflow, carries a weight, drag, and ultimately a fuel economy penalty. And it's not just fuel, it's about utility. A Ranger Raptor weighs over 900 pounds more than a standard 4x4. The direct result? Its payload capacity gets slashed by nearly 350 pounds. Every pound of hardware we add for this cooling system is a pound of gear the customer can't carry. That is a direct trade-off we have to own. So, after looking at all the data, the simulations, and the very real trade-offs, where do we go from here? Let's talk about the path forward. Here is our action plan. First, we are officially pursuing the series OTA concept as our primary solution. Second, the packaging team is tasked with investigating relocation options for the ECU. This is a top priority. Third, we need to develop and simulate air guides and ducting for that bumper location to maximize every bit of airflow we can get. And finally, we need a full system-level simulation to quantify the hit we're going to take on fuel economy and aero. So I'll leave you all with a question that really sums up this entire project. How do we engineer the incredible performance our customers are demanding without sacrificing the real-world efficiency and utility they actually need every single day? Answering that question is what this team does best. Let's get to work.